Welcome back to this course on climate change, and what we're going to cover in today's lecture is following on from what was in the last lecture about energy and power. We're now going to talk about how energy received on the Earth from the Sun balances energy lost from the Earth and how that then leads to the temperature of the Earth. And the first thing we're going to do is look at, if you like, the differences between the three Earth-like planets in the solar system, the differences between planet Earth and Mars and Venus, particularly then looking at the energy balance, the balance between the amount of energy received by the planet from the Sun and then the energy lost back out to space, and also this concept of albedo, or the amount of sunlight that's reflected. So let's now look at the three different Earth-like planets. They actually started off as planets with almost completely carbon dioxide atmospheres. The atmospheres originally had much the same composition. Mars is the furthest planet from the Sun. It now has still an atmosphere which has almost completely carbon dioxide, but the amount of the atmosphere is actually very, very thin. The atmospheric pressure on Mars is very small. The Earth has an atmosphere which only has 0.03% carbon dioxide, now actually closer to 0.04% carbon dioxide. We'll talk about that more when we talk about how carbon dioxide is increased. And our surface temperature on the Earth is on average about 15 degrees Celsius on average. And we're also going to compare this with Venus, closer to the Sun and a lot hotter atmosphere. And these temperature increases that we're going to be looking at are due to the density of the atmosphere, or the pressure of the atmosphere, and the amount of carbon dioxide in the atmosphere. And the atmosphere on Venus is more than 90% carbon dioxide, and it has what we call a very strong greenhouse effect, almost a runaway greenhouse effect, and the surface temperature on the planet is very, very high. So what we're going to look at now is this impact of how much sunlight is received on the planet's surface and the effect of loss of heat, and how we can work out what the temperature of the planet would be without any atmosphere, without any greenhouse gases. So let's think about this. We've got sunlight coming in from the Sun. The amount of sunlight depends on the distance from the Sun and decreases proportional to the inverse of the square of the distance, or 1 over the distance squared. And then the sunlight will be absorbed in the Earth's atmosphere and at the Earth's surface. Some of it will be reflected from clouds, some of it will be reflected from the Earth's surface, but what isn't reflected will be heating up the Earth's atmosphere and heating up the Earth's surface. And as it heats up the Earth's surface, the Earth will radiate out heat radiation, or infrared radiation, or long wave radiation. And there's going to be a balance between the amount of energy that's absorbed, or the difference between the energy received from the Sun and how much is reflected, and the energy that is essentially re-radiated. And that balance between the energy reflected plus the energy absorbed is got to be equal to the energy that's input, and that will end up with a temperature balance in this system. So how much is reflected, particularly how much sunlight is reflected, is determined by what we call the albedo. It's a fancy name, but it just means what fraction of the incoming sunlight is reflected by the surface. And we know that white surfaces, like clouds, are highly reflective, or snow and ice are highly reflective. They have high albedos. For cloud, between 0.7, 0.8, 0.9, sometimes less if it's very thin cloud. Snow is highly reflective. Water, when the sun is overhead, is not reflective at all. Water looks dark, sometimes dark green, sometimes dark blue, but it's dark. However, when the sun is at a very low angle, it can actually reflect, and you'll get sunlight scattered, or the water acting like a mirror. Bare ground, dirt, doesn't really reflect at all. dry ground or dust and sand can be highly reflective, albedos of the order of maybe 0.4 or so. Black surfaces have very little reflection. Surfaces like soot or charcoal, anything that looks dark has little reflection, has a very low albedo, and on average, when we combine together the impacts of clouds, the Earth's surface, the oceans, and deserts and snow and ice, the average reflection of all the surfaces on the Earth is about 31%. In other words, about 70% of the sunlight received on the surface of the Earth is absorbed, and about 31% is reflected. So now, the energy in the light, in the sunlight, depends on the temperature of the source. And so when we look at the range of different colours, that will affect the energy and will be dependent upon the source temperature. So we look at these range of different colours, and the longest wavelengths are in the red colours, or even longer wavelengths are infrared. And they are associated with long wavelengths and lower temperature sources, whereas the shorter wavelengths have higher energies and they're associated with higher temperature sources. And we can look at those temperatures in terms of the peak emission temperatures. We know that if we're in a fire or an intense source of heat, the colours that will come from that fire will be whiter the hotter the source. And the lower temperature source, it'll be redder colours. And that's exactly the light dependence. Low temperature sources have red light. Even lower will be what's called infrared or longer wavelengths. And the surface of the Earth only produces or releases energy in infrared wavelengths. We can't see them. So now what we're going to do is look at how the sunlight, the light from the sun, what its amount of energy is and its wavelength. The sun has a very high emission temperature, nearly 6,000 degrees Kelvin. Light from the Earth is coming from a source at around 290 or 300 degrees Kelvin. What that means is the light from the sun is in short wavelengths or visible wavelengths and is very high intensity, whereas the wavelengths for light from the Earth is infrared wavelengths and much lower intensities, much lower power in terms of watts per square metre. Now the intensity of the energy coming out from an object like the sun goes as the temperature to the fourth power. So the Earth, which has a much lower temperature, only a temperature of around 3,000 degrees Kelvin, has effectively an emission which is only about 400 watts per square metre, whereas the emission from the sun, because it goes as the temperature to the fourth power, is many, many orders of magnitude greater. Now, the energy from the sun diminishes as the sunlight spreads out, coming out from the sun, and by the time it reaches the Earth, it's only around 1,376 watts per square metre. And, not much greater than the emissions from the Earth. But the energy emitted from the surface of the Earth is many orders of magnitude greater than the energy emitted from the surface of the Earth, and that's because temperature affects the intensity of the emitted radiation. And that temperature variation is not linear, but to the fourth power of temperature. So the temperature increases and the emitted energy increases rapidly. Temperature falls, emitted energy falls dramatically as well. So what we're going to do now is look at considering the Earth as what we call a perfect black body. Those relationships that I talked about just a minute ago, how much energy is emitted from an object depending upon temperature to the fourth power, is what we call an ideal black body, a perfect round body emitting as much radiation as possible. And what we're going to do is look at the simple balance between the energy emitted and the energy absorbed. Now, unfortunately, this is going to have a few equations in it. And the first thing we're going to do is work out how much energy is emitted by the sun and absorbed at the surface of the Earth. The first thing we have to do is work out, okay, how much that energy received at the top of the atmosphere is going to be absorbed. For an albedo of A, reflectivity of A, the amount of sunlight absorbed is 1 minus A. The intensity of the sunlight at the top of the atmosphere is called this letter S, and that's about 1,376 watts per square metre. And then we have to work out what the cross-sectional area of the Earth is that's going to absorb sunlight. Effectively, that's a disk, which is the cross-sectional area of the surface of the Earth. And so if we look at this equation here, it's pi times the radius of the Earth squared. That's the cross-sectional area. So that's the total amount of sunlight from the solar beam at the distance of the Earth from the sun, which will be absorbed by the Earth. 1 minus A times S times pi r squared. And then that's going to be balanced by the loss of energy going out to space from the surface of the Earth. Remember, a black body emits heat radiation or infrared radiation at sigma times the temperature of the black body to the 4th power. Let's say that the average temperature of the Earth is T subscript E. Then the amount of infrared radiation in watts per square metre being emitted is going to be sigma times TE to the 4th power. And that's then multiplied by the total surface area of the Earth. And the Earth is essentially a round ball of radius RE squared, and the surface area of the Earth is 4 times pi times RE squared. So then what we're going to do is look at how we can simplify this equation and maybe solve for the temperature of the Earth, the average temperature of the Earth, that would be in balance with the amount of incoming sunlight that's absorbed and the loss of heat radiation. So we can do some cancelling. We can cancel out the pi's on both sides of the equation, pi here and on the other side of the equation. We can cancel out the radius of the Earth squared. And that leaves a much simpler equation. It gives us, when we insert the albedo and the amount of sunlight that's coming in, 1 minus 0.31, because 0.31 is the albedo, times the intensity of the sunlight at the top of the atmosphere, 1,370 watts per square metre. This constant sigma is what's called the Stefan-Boltzmann constant. You don't have to know what it is. But what we can do then is solve for this temperature of the surface of the Earth. And when we do that, the answer is the equilibrium temperature of the surface of the Earth if there was no atmosphere, if there was a balance between incoming sunlight and loss of heat radiation, would be 255 degrees Kelvin. Now the Celsius scale, 0 on the Celsius scale, is 273 degrees Kelvin. So this balanced temperature for the Earth is minus 18 degrees Celsius. And that would mean that the Earth would essentially be too cold for life on almost all parts of the Earth, or the Earth would be snow covered. Now we know that the Earth doesn't have an average temperature of minus 18 degrees Celsius. In fact, the Earth's temperature is about 15 degrees Celsius. And there's something going on which means our approximation, this black body approximation, is wrong. And that difference is there are gases in the atmosphere. Radiation by gases in the atmosphere is called the greenhouse effect, and that's what's critical for the Earth's temperature being 15 degrees Celsius, for the temperature on Venus being 500 degrees warmer than you'd get from a balance with no atmosphere. And actually the greenhouse effect is really negligible on Mars, and the average temperature on the surface of Mars is below freezing. So, yes, temperatures on Mars and Venus can help us understand about the energy balance between different surfaces, the balance between the incoming sunlight and the outgoing heat radiation. And we know that the energy coming in must balance the energy going out. And there's going to be a temperature dependence. The more energy coming in, that means that to balance with energy going out, there must be a warmer temperature of the surface of the planet. As we go further away, like to Mars, there's a colder temperature on the surface because we're further away from the sun. Simple physics, what's called black body radiation, tells us how much energy a body's going to radiate. And we know that the incoming sunlight from the sun is going to warm up the surface of the Earth, both warming up the atmosphere from the sunlight that's absorbed in the atmosphere and warming up the surface of the Earth. And then the Earth and the atmosphere are going to lose heat radiation. And that heat radiation will be partly absorbed in the atmosphere, and that's what's called the greenhouse effect. And we're going to cover this much more in the next lecture.